Thanks, Vinod, for the kind introduction, and thanks to the organizers for organizing this really nice conference at a wonderful venue and inviting me. So today I'm excited to tell you about some recent work that we have been doing on realizing electrical switching of spin and valley on the theory side by inducing spin-orbit coupling in rhombohedrally stacked graphene. So before I begin, this work has been mainly led by my collaborators Taige and Mark from UC Berkeley, and also we have benefited from conversations with Mike Zalatul, and it's appeared recently in this PRL. Okay, so for this audience, I probably don't really need to provide much of a motivation for why we want to use electric fields to control magnetism, but just so that we are all on the same page. So in magnetism in materials, as we know, is typically controlled by magnetic fields, and these magnetic fields are sourced by currents in solenoid, which is a dissipative process, so it requires a lot of energy to run these currents. They generate Joule heating, and as a result, electrical control has been a long-standing goal of the spintronics community because it promises more energy efficient devices. So what we want is that we have some spin, we apply an electric field, and then the spin switches. But doing this is not so easy in practice because of the physical origin of magnetism. So in most material systems, magnetism originates from a combination of Fermi statistics of electrons and the repulsive Coulomb interaction between electrons. And if you see, none of these things are directly controllable by electric fields. The statistics you can't control. The Coulomb interaction as well is not directly controllable by electric fields. So in recent times, though, atomically thin 2D materials have emerged as a very highly tunable platform for studying a lot of correlated physics. And one nice thing about these materials is that you can get really different material properties by using different stacking. So you can play this game of quantum Lego, this nice picture I took from this review article by Gaiman Grigoriev. And using these different stackings, you can get very different properties. So let me give you a couple of examples. So for example, you can vary the carrier density using a metallic gate, which allows you to explore a large number of phases in the phase diagram as a function of doping in situ. You can also stack on some dielectric material and therefore vary interaction strength. And this allows one to study the competition between Coulomb interaction and bandwidth or kinetic energy. More recently, we have found that there is a new tuning knob, which is this twist angle between layers. So these materials are what are called moire materials. Xiaodong talked about some of them in the context of TMDs. Here I'm showing you a picture of bilayer graphene, where you add a small twist angle, and that also allows band structure engineering due to subtle interference effects and creation of flat bands and also topological bands. Finally, we can also apply perpendicular electric fields. These are called displacement fields. Again, Xiaodong talked about it nicely, so I don't really need to introduce it. But they can be used to flatten bands and engineer band topology as well. So the net effect of doing all of these things is that one can really exchange interaction relative to the bandwidth. So in the Hubbard language, one would say that T over U, where U is the effective interaction strength, and T you can take as the hopping, is much smaller than 1. That allows one to see enhanced correlation effects, although that language may not be appropriate in all cases because one may also have topological bands. But nevertheless, different forms of hybrid correlated states are present, and in particular, different forms of magnetism naturally appear in these materials because of enhanced interactions. So these include orbital or Chern ferromagnets, quantum anomalous Hall states, like the one Xiaodong talked about, also spin polarized ferromagnets as well. So now that we have this kind of ferromagnetism in these 2D materials with a large degree of tunability, one question one may naturally want to ask is whether we can exploit the tunability of van der Waals heterostructures to design some electrical switch of magnetism. More precisely, in a lot of these materials, including graphene and TMDs, one has both spin degrees of freedom and valley or orbital degrees of freedom. And one can ask whether one can selectively control the spin and valley degrees of freedom. So that is what this talk is going to be about. We are going to propose a mechanism for selectively switching a particular spin or valley just by reversing electric fields in chiral or rhombohedrally stacked multilayer graphene. And I will explain what that means as I go along. All right, so this is a brief outline. So I will first discuss substrate-induced spin-orbit coupling in chiral few-layered graphene, and move on to discussing design principles of an electrical spin and valley switch using these kind of structures with interaction-induced polarization or ferromagnetic polarization, and end with some conclusion. So let's jump in. So what's chiral multilayered graphene? Where it's a particular stacking, where each adjacent layer is displaced by a certain amount with respect to the previous layer so that they don't exactly overlap. So the most popular example is the case where you have two layers. This is the stable structure. It's called Bernal bilayer graphene. You can also have three layers, which corresponds to rhombohedral trilayer graphene, or RTG, where you have the same relative displacement between any pair of layers, the first two and the second two pairs. And when I started working on these were the ones which people were making and doing experiments on, but recently people have made 4 layers and also pentalayers of these materials. So this stacking is relatively stable, at least on the time scale that you can do experiments on them. Okay. So it's important to note that in these materials, the active sites for the low energy physics are A1, which refers to one of the sublattices on the top layer, and Bn, which refers to the other sublattice in the bottom layer. And the reason is that these 2 points, A1 and Bn, here I'm showing it for 3 layers, they don't lie directly on top of any other sublattice in an adjacent layer. So another way to think of this is that in this picture for n equals 3, B1 and A2 strongly hybridize with each other because of the interlayer tunneling. So they create bonding and anti-bonding orbitals which go outside of the low energy manifold. And similarly for B2 and A3. So all the low energy physics can be thought to happen in an effective subspace defined by A1 and B3. So within this subspace, you can write down an effective Hamiltonian, and you get a term which is similar to Dirac cones but with higher order band touching. So this is a very simplified model, of course. Again, in real materials, it's going to be slightly different because of anisotropies that I haven't accounted for. But the simple model gives us good intuition for the physics. So you get a term which is of the order of k to the n in the dispersion, so an nth order band touching at both the k and the k prime points. And now you can add an additional displacement field or a perpendicular electric field to further enhance the density of states. So on the left, I'm showing you a plot of the density of states at 0 electric field and finite electric field. And you can see that it's really sharply enhanced once you add a finite amount of displacement field. And this is important because a large density of states naturally promotes flavor polarization. So as I was saying, this enhanced density of states leads to interaction-driven flavor polarization, which you can think of as Stoner ferromagnetism. That's the case for most of these materials, I believe. But there are also some experiments from the Göttingen group here, which shows that some of these states may be partly insulating and not fully metallic. Nevertheless, most of the experiments are actually showing reasonably well conducting states. And the picture is that if you have small displacement fields, then the density of states is not large enough, at least for the bilayer or trilayer. So you have 4 Fermi pockets, 2 per valley and 2 per spin. And once you turn on a large displacement field, then it flavor polarizes into a single state, a single Fermi pocket, which is both spin and valley polarized. There are also other states that I won't be talking about because the singly spin and valley polarized state will be the main player in this story. Okay. So now we need to discuss what happens when you induce spin-orbit coupling, because without spin-orbit coupling, which is quite weak in graphene, the spins are kind of free to point in any direction. So we want to encapsulate these chiral stacked graphene by some TMDCs, or transition metal dichalcogenides. And if we just think of the spin-orbit coupling induced by TMDCs, which are insulators, onto the adjacent monolayer graphene, DFT calculation shows that there are 2 major contributions. The first one is this easing form of spin-orbit coupling, which locks spin and valley together So if I call tau valley and S spin, it's a tau z S z kind of term. And this reduces the full spin rotation symmetry from SU2 to U1. In addition, of course, there is also a Rashba term, which breaks spin rotation symmetry completely and also hops between adjacent sublattices in the same layer. So sigma x here is a term which denotes hopping from A sublattice to B sublattice in one layer. And these terms are all of milli-electron volt scale, and I think we still don't have a consensus as to what the exact magnitudes of these terms are, whether one is larger or smaller. So this is where the chiral structure comes to really play a role, because in order to talk about spin switching, we first need to have some conserved spin degree of freedom. And it's not present in terms once one has a Rashba spin orbit coupling. However, I argued to you previously that only one sublattice on the top layer and the other sublattice on the bottom layer really matters for the purpose of our story. The intermediate sublattices have really very low weight on the low energy wave functions because of the formation of these bonding and anti-bonding states. So if you treat these spin orbit coupling terms as a perturbation, you will see that the Rashba term really contributes at a higher order in perturbation theory because it hops between two adjacent sublattices. And the upshot of this is that you can get a term of the order of lambda Rashba squared divided by this hopping. This hopping is order electron volts, like 0.5 or 0.4 electron volts, so it's a very large scale. So this Rashba term can more or less be neglected, at least at low dopings, and therefore you have only E-sync spin orbit coupling in this system with chiral stacking. So with this, we can write down again an effective Hamiltonian in this A1Bn basis. And it's the same Hamiltonian that I showed you before, except that if you now encapsulate it by two TMDs on the top and the bottom, you will have a lambda top and a lambda bottom induced spin orbit coupling, E-sync type, into the bottom layer and top layer of the graphene itself. You can ask me whether this is a good approximation. So we did calculate the band structure with using all the trigonal warping terms which I have neglected in this effective Hamiltonian, and also the Rashba term. And if you keep comparable magnitudes for the E-sync and the Rashba term, you will see that the spin SZ expectation value is almost close to 1 near the K and K prime points where I have plotted these bands or line cuts of these bands. So this is indeed a fairly good approximation, at least when you are at low doping. Of course, things get different when you go to higher dopings. Okay, so now you can ask, what is the effect of the relative alignment of the TMDs when you induce this kind of spin orbit coupling? Note that here I'm not talking about the alignment between the graphene and the adjacent TMD. Their lattice scales are quite different, and we will be neglecting that particular effect, which has been shown by DFT to be a reasonable approximation. So if the TMDs on the top and the bottom are aligned with each other, then you expect that the sign of the E-sync spin orbit coupling is the same on both the top and bottom layers. So lambda I top is the same as lambda I bottom. You can also imagine the scenario where they are exactly anti-aligned with each other because TMDs have no C2 symmetry, as Xiaodong showed. So if they are anti-aligned, then the system has a particular inversion symmetry, and it's preserved at zero electric fields. Of course, a perpendicular electric field will break that, but at least at zero electric fields, it has an inversion symmetry. And this constrains opposite signs of E-sync spin orbit coupling on the top and bottom layers. So if they're aligned oppositely, then the sign is also opposite, which makes it easier to remember. However, this can be shown rigorously. The previous statement about aligning them parallelly and having the same sign is not a rigorously proven statement, but we expect that to be true. So now I have spin orbit coupling. I can add an electric field which enhances density of states, and that leads to flavor polarization. It requires finite displacement fields in Bernal bilayer or rhombohedral trilayer graphene. Here I'm plotting a phase diagram from Hartree-Fock at lambda E-sync equals 2 MeV in the aligned device. And you will see that there are phases which correspond to spin and valley polarized phases, and then again spin and valley locked phases where you have two Fermi pockets. In rhombohedral pentalayer graphene, which is more recent, you can see such correlated phases even at zero displacement fields. On the experimental side, you may ask whether such structures have been realized. So indeed, again, there is work from the Caltech group of Stefan Najperke and also from Thomas White's group in Göttingen, and on the pentalayer side from Longju's group in MIT, which shows that you can indeed realize such heterostructures and measure them. So what are these different phases? The spin valley polarized phase is the one where I have a single Fermi pocket. That's the yellow part. You can also have spin valley locked phases where you have two spins, as one spin per valley, but they are kind of locked to each other. This is not, strictly speaking, a symmetry broken phase when I have finite Ising spin orbit coupling, but it's really enhanced by interaction effects. One can also get some partially flavor polarized phases and IVC type of phases, which I won't really mention because they are not the focus of this talk. I'll mostly focus on the spin valley polarized phases where you have polarized all your electrons into a single spin and valley flavor. And then we can ask what kind of spin and valley flavor they are polarized in, and that depends on the sign of the Ising spin orbit coupling, which you can think of as an effective weak magnetic field acting on this. And let's say that it favors spin valley locking such that tau times S is equal to 1. So I can start with electrons in one layer. I can now switch the displacement field, which moves them to the other layer. So in the aligned device, that means that I see the same sign of spin orbit coupling, and I want to preserve tau S equal to 1. But there are still two options with tau S equal to 1. One of them is, let's say I have an electrons in valley K, spin pointing up. The other is I have electrons in valley K prime, but spins pointing down. So it still doesn't give us the kind of control that we want. It might choose between these two pairs of states, but ideally we would like to flip the valley and spin on demand by switching this displacement field. So in order to do that, what one really needs to do is to somehow split this degeneracy between K up and K prime down. These are related by time reversal symmetry. So the simplest thing we can think of is to add a constant perpendicular magnetic field B. Note that this field doesn't need to be switched or anything, and it can be very tiny in magnitude. It just needs to remain there to select one of these states. So this magnetic field B can now couple to both orbital and spin degrees of freedom by the spin G factor GS and the valley G factor GV. And most importantly, the valley G factor actually depends on the direction of the applied displacement field. This is because the sign of the Dirac mass at K and K prime points is determined by the direction of this perpendicular displacement field. So switching this switches the sign of the Dirac mass, which affects the Berry curvature and also reverses the orbital magnetic moment. So in particular, in this material, if GS is much smaller than GV, which I will show to you later is the case, then the orbital magnetization is actually pinned by the magnetic field. So if you move from one layer to the other layer, the valley and spin are both flipped. So let me explain this in a particular setting. So let's assume that GS and GV are both positive, and let's also assume that the electrons are in the upper layer and K up is occupied when the displacement field points up. So now I want to switch the displacement field so that it points down. The electrons move to the opposite layer. We have the aligned device, so they feel the same sign of the spin orbit coupling. But because I have switched the displacement field, I have also reversed the sign of the Dirac mass, and as a result, I have switched the sign of the valley G factor. So now I definitely want to move to the opposite valley, but valley is locked with spin. So because I'm moving to the opposite valley, I'm also moving to the opposite spin flavor. So this is an electric field induced. Sorry, I think I'm showing the wrong slide here. So yeah, sorry, this is the one. So in this case, we have an electric field induced spin plus valley switch, where I move from K up to K prime down by just reversing my displacement field. I don't need to touch the magnetic field. So you can play the same game in the device with anti-aligned TMDs, where again, let's say you start with K up. Now if I flip the displacement field, my electrons move from the top layer to the bottom layer. However, now they will see the opposite sign of spin-orbit coupling. So the low energy manifold is different. If the initial low energy manifold was k up and k prime down, now the low energy manifold is k down and k prime up because of the opposite sign of spin-orbit coupling. Again, I want to flip valley because the sign of the valley G factor has reversed. So if I was in valley k, I want to move to valley k prime, but now that comes with the same spin. So I have essentially switched valley without switching spin in the device where I have anti-aligned TMDs. Finally, the point that I would like to make is that this typical value of GV over GS is quite large in chiral graphene, and it is also tunable. So we can control the ratio by tuning either the displacement field, which localizes the orbital. So intuitively, that gives you small Berry curvature and smaller value of the valley G factor. We can also go to larger number of layers, and that leads to a higher order band touching in the simplified model that I presented. So it has a larger Berry curvature and also has a larger GV. So by changing either the displacement field or the number of layers, one can tune the ratio. However, in the region where these kind of correlated states are seen, we can numerically evaluate the valley G factor, and it varies between like 15 to 30, which is much larger than 2, which is the case for just the spin G factor. So we have numerically confirmed this by evaluating this valley G factor in the fully microscopic model, including trigonal warping and higher bands. And indeed, this is true. So we are in the regime where the valley G factor dominates which direction or which valley we want to be polarized in. So all the physics that I told you previously goes through. So you might ask me, I showed you a spin plus valley switch. I showed you a valley switch as well, but can I just switch spin without changing valley? And indeed, that can also be done by just using electric fields. But here one needs to reverse the chemical potential so that one goes from electron doping to hole doping. And so we can do the complete trifecta, switching both spin and valley, switching just spin polarization or switching just valley polarization by just using electric fields, using the same principle. Okay, so this brings me to the end of my talk. So I discussed the effects of induced spin orbit coupling in chirally stacked graphene or rhombohedrali stacked graphene. And I argued that this induced spin orbit coupling plus electric field induced correlations can lead to a selective spin or valley switch. So there are a few open questions. Maybe one of the most important open questions for practical purposes is how stable are these phases, polarized phases to thermal fluctuations. We did Hartree-Fock. We got a reasonably sized gap, order 5 to 10 MeVs, but Hartree-Fock definitely overestimates the gap. So we need more unbiased numerical methods to see if they are stable to larger temperatures or whether they disappear below 10 Kelvin or 5 Kelvin. Another important question, which has partly been answered by Longzhu's work, is whether one can use these correlations and induced spin orbit coupling to create a stable magnetic memory. So recall that in our case, that story that I told you requires a displacement field to have polarized phases first of all. So that means that you need to have your power constantly on. If you switch it off, you turn off the displacement field and polarization goes away. However, in this device with pentalayer graphene, you do see correlated phases even at zero displacement field. So you can combine that with some spin orbit coupled substrate to have a magnetic memory which remains when you turn the power off. And finally, maybe one can do this in intrinsically more devices with spin orbit coupling that allows for a higher degree of tunability. So we have some work on that, and I would be happy to talk to you about later if you are interested. So that brings me to the end of my talk. Thank you very much for your attention, and I would welcome any questions.